I think. Okay, let me begin. What we'll do is just review some of the material we've probably already covered. Comparing populations is an important part of statistics. Quite often you have populations, two or more populations that you want to compare. The quantity that you might want to compare is proportions in a group between the two populations, or comparing the means of two populations. You also might want to compare the variances of the two populations. So most studies have more than one population. Here's probably one of the biggest experiments ever. It was the Salk vaccine trials in 1954. This was a vaccine that would reduce the incidence of polio. Polio was a devastating disease for both young adults and older individuals. There was two populations. One were given the vaccine, the other one given the placebo. So, something that wouldn't have an effect. And one wanted to compare these two populations. There's an important fact in combining random variables. If you have two independent random variables and they're both normally distributed, the difference will be normally distributed with the mean equal to the difference in the two means. The standard deviation is a little bit more complicated. It's the square root of the two standard deviations squared and added together. This allows you to find the, if you have two statistics and you want to look at the difference is a good way of comparing what the two statistics are measuring. This allows you to find the distribution of that difference. Comparing proportions. So we have two populations, 1 and 2. P1 is the proportion in population 1. P2 is the proportion in population 2. And the objective is to compare the two proportions. Are the two proportions equal or are they different? Is one bigger than the other? The test statistic is that you use the two sample proportions, P1 hat and P2 hat. They're both estimating P1 and P2. That will have a normal distribution using the fact that I said before. The mean will be equal to the mean of P1 hat and minus the mean of P2 hat, P1 minus P2. So that difference will be estimating the difference in the two proportions. The standard deviation of that difference is the square root of P1 hat squared plus sigma P2 hat squared. That's P1, 1 minus P1 over N1, P2, 1 minus P2 over N2. And if you don't know the proportions to calculate sigma d, you might have to use the sample proportions in their place. Then if we then can standardize d, divide by, subtract off its mean, divide by its standard deviation, that will have a standard normal distribution. So there's the statistic that will have a standard normal distribution. The difference in the two sample proportions minus the difference in the two proportions they're trying to estimate over the standard deviation of the difference in the two proportions, which is approximately P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over, that should be N2 there, square root. We can use that to test whether the proportions are equal against a two-sided alternative or possibly a one-sided alternative. If P1 and P2 are the same, P1 minus P2 will be equal to 0. And P1 and P2 can be replaced by their common value. Since their common value won't be known, it can be estimated by the total number of successes in the combined two samples. Comparing proportions again, there's the test statistic for testing whether or not P1 and P2 hat are the same. There's the critical regions. The way that test statistics have been set up, it's been set up to have a standard normal distribution if P1 and P2 are the same. Depending on the alternative hypothesis, whether it's one-sided or two-sided, you'll use either a two-tail test or a one-tail test. Here's an example. In this study, this was done several years ago, one was interested in whether pipe smokers had a higher death rate than non-smokers. We know that cigarette smokers have a much higher death rate than non-smokers. Now we're doing the same thing for pipe smoking. There was 1,067 non-smoking pensioners, male pensioners, who never smoked, and 402 male pensioners who smoked a pipe for more than 6 years. So both of those groups were observed for 5 years, and number of deaths that occurred was counted. 117 in the non-smoking group, 54 in the pipe smoking group. Is the mortality rate for pipe smokers higher than for non-smokers? That's the question. So we wanted to, the alternative is that non-smokers have a less mortality rate than for pipe smokers. It's a one-sided alternative, so it'll be a one-tail test. There's the test statistic, P1 hat minus P2 hat. And on the bottom, we have the standard deviation of P1 hat minus P2 hat when the two proportions are the same. there's the calculation of P1 hat. P2 hat is a little bit higher, 13%. For non-smokers is about 10.97%. If the two proportions were the same, they can be estimated by the total number of deaths in the combined two samples over the total number of cases. So there's the test statistic. We plug in these numbers. We get a critical value. We're going to reject if Z is less than minus Z sub alpha. We're going to reject for a negative value because that's what we'd expect if HA was true. It's minus 1.645. We compare that with the, well, that's the critical value. We compare that with the exact value. It's not less than that. So we accept H naught. Conclusion, there's no significant increase in mortality rate due to pipe smoking. That doesn't mean that there isn't an increased mortality rate, but this experiment did not find it. Estimating the difference in two proportions. So we have two populations, we have P1 and P2, and we want to estimate the difference between P1 and P2 with a confidence interval. This is the formula for the confidence interval. It's P1 hat minus P2 hat plus or minus Z sub alpha over 2 sigma P1 hat minus P2. The standard deviation of P1 hat minus P2 hat is P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2 square root. When we're testing, we're assuming the null hypothesis was that the two were the same. So we had to combine, get an estimate of the common value. So an example, in the same example as we used before, we've got P1 hat and P2 hat. P2 hat is the mortality rate for pipe smokers. P1 hat, the mortality rate for non-smokers. Putting those numbers in, the confidence interval is 0.0247 to plus or minus 0.03. That's minus the number to plus a number. So that interval contains 0. So the difference could be 0. So here's just a summary. There's the test statistic for testing whether two proportions are different using this two sample proportions and the overall proportion of success in the combined samples, P hat. There's the formula for estimating the confidence interval for P2 minus P1, P2 hat minus P1 hat, plus or minus Z sub alpha over 2 sigma P2 hat minus P1 hat. And that's what's underneath the square root symbol. Comparing means. So now we've got two normal populations. They possibly have a different mean and a different standard deviation. We take a sample from population 1 to get information about mu1. Those are the X values. And it'll also give us information about sigma 1. And a sample from population 2. Quite often the sample sizes are equal, but that's not necessarily the best way. Sometimes you choose the sample size 2. Sometimes it's less costly to take it from population 1 to population 2. So you choose the sample sizes so that you get as accurate an estimate as possible and minimize the total cost. So we have to take into account the sample sizes might not be equal. We want to test whether the means are equal against them not equal. Or we could be trying to pick out a one-sided alternative. Again, the alternative is the research hypothesis. It's what the researchers trying to prove. Consider this test statistic, x bar minus y bar over the standard deviation of x bar minus y bar. The standard deviation of x bar minus y bar is square root x sigma x bar squared plus sigma y bar squared. Sigma x bar squared is sigma 1 squared over n. Sigma y bar squared is sigma 2 squared over n. And if we don't know sigma 1 and sigma 2, we have to replace them by their sample estimates. If H naught is true, this statistic will have a standard normal distribution, even when the sample standard deviations are replaced by their estimates. And if that's the case, we require the sample size to be large. This has a standard normal distribution. There's the estimators of U1 and sigma 1, U2 and sigma 2. Now, if Z has approximately a standard normal distribution, the critical region is chosen from underneath the standard normal curve. Here's an example. We're interested in if an exercise program has some positive effect on reducing high blood pressure in patients who have abnormally high blood pressure. So 500 patients with abnormally high blood pressure are put on the exercise regime. A second sample of 400 patients were not required to adhere to the exercise regime. And after a period of 1 year, the reduction in blood pressure was measured for each patient. If the not putting them on an exercise regime had no effect on their blood pressure, the average blood pressure drop in blood pressure would be 0. But it might happen that just being in the study causes them to reduce blood pressure. So the null hypothesis is that the exercise group did not have a higher average reduction in blood pressure. The alternative is that they did. That's what the researcher is trying to prove. There's the test statistic. Suppose the data was collected, X bar, Y bar, SX, and SY were all calculated. You put those into the test statistic. Turns out to be 10.4. Going to reject that if Z is greater than Z sub alpha. It's going to be a one-tail test. We don't divide alpha by 2. Put all of the value of alpha into the upper tail. The value of Z is quite a bit greater than 1.645, so we reject H naught. Conclusion, there is a significant effect due to the exercise regime on the reduction in blood pressure. It's much higher for those who've adhered to the exercise regime. Estimating the difference in means using confidence intervals. So confidence interval for mu1 minus mu2 is the estimate of mu1, which is x bar, minus the estimate of mu2, which is y bar, plus or minus z sub alpha over 2 times the standard deviation of the statistic mu1 hat minus mu2 hat. That is square root sx squared over n plus sy squared over m. So in the example, x bar was 10.67, y bar was 7.83. SX was 3.895 and SY was 4.224. The sample sizes were 500 and 400. When we compute this confidence interval, the confidence interval is well on the positive side of the axis, agreeing with the statement that the difference is going to be that the one for X bar was significantly higher than the one for Y bar. Now, when you have small sample sizes and you don't know the standard deviation, you have to estimate it. The distribution of the test statistic changes from the standard normal distribution to the t-distribution. So this is comparing means with small sample sizes. It is called the two-sample t-test. So you have two populations. The mean of population 1 is mu1, the standard deviation sigma 1. The mean of mu2 of population 2 is mu2, standard deviation sigma 2. We don't know mu1, mu2, or sigma 1 and sigma 2. We have data from both populations which will be used to estimate those. The objective is to compare the two population means. We'll also later on give a test which compares the two standard deviations. So we want to test if mu1 equals mu2 against alternative. It could be a two-sided alternative, or it could be a one-sided alternative. There's the test statistic. That has a standard normal distribution. If the sample sizes are large, this statistic here, where I will place standard deviations by their estimates, this will have approximately a standard normal distribution, but only if the sample sizes are large. This will not be the case if the sample sizes are small. So we'll look at one where the t-test for comparing means, small samples, but equal variances. Quite often the variance of the two populations is the same. Quite often the two populations result in two different treatments that can be applied. The treatment may affect mean, move it up or move it down, but might not affect the standard deviation. This is the measures the variability of subjects receiving the same treatment. So this one, we're assuming that the variance is the same. There is the sample statistics. This will estimate at mu1. This will estimate mu2. Y bar will estimate mu2. Both SX and SY will be an estimate of the common variance. They estimate the same thing. They can be combined in what's called the pooled estimator. We square SX, square SY, multiply by the degrees of freedom, and then divide by the total degrees of freedom, n plus m minus 2. So this is a weighted average of SX and SY. Both of them are estimating sigma. This is probably a better estimate of sigma. Put that into the formula. And this statistic can be shown to have, if H naught is true, t-distribution, the degrees of freedom is n plus m minus 2. So that's where we look up critical values under the t-distribution, degrees of freedom n plus m minus 2. There's the critical region. It could be two-sided if the alternative is two-sided. It could be just one-tailed if the alternative is one-sided. Here's an example. We're interested in a drug reduces the size of a cancerous tumor. So we have 9 test animals. 3 of them are given the drug, 6 of them were left untreated. So They were implanted with cancerous tumor. Then they observed for a period of time, and the tumor size was measured after the test period. So we want to test whether the treatment had no effect or possibly had a negative effect. Against the alternative, the treatment did have a positive effect. The average tumor size after with the treatment was smaller than the one that didn't have the treatment. There's the test statistic. Here's the data. We have measurements of tumor size that were treated with the drug. They look to be a little bit smaller. There's the tumor size, the 6 tumor size of 6 animals that were left untreated. The average for the drug treated was 1.657. The average for the lower one, for the ones that were left untreated, was 1.9. There's the standard deviations, both approximately the same. So the assumption of equal standard deviation looks to be correct. We're now wanting to know what it means. This difference could have occurred by chance. Took another 6 animals, another 3 animals, could get it the other way around. There's a scatter plot. The red ones are the ones that are treated with the drug. The blue ones are the ones that were left untreated. The pooled estimate of variance, both SX, which is 3.215, and an SY, which is 3.36393, are estimating common value sigma. This is how you combine them to get the best estimate of sigma. It's somewhere in between the 2 values here. So that's the number that goes in the formula for T statistic. The T statistic turns out to be minus 1.025. We expect it to be negative if the drug treatment was smaller than the untreated ones. To find out whether it's significantly smaller, we look up critical value minus 1.895. So we would have declared it to be significantly smaller if T turned out to be less than minus 1.895. Wasn't, so we ended up accepting. The null hypothesis is that the drug treatment wasn't significantly smaller than the untreated animals. Confidence limits for a difference in 2 means. Small sample sizes. It's the difference plus or minus T sub alpha over 2. Critical values coming from the T distribution. The degrees of freedom is n plus m minus 2. S pooled is the pooled estimate of sigma. So that's how confidence limits are calculated in the cases of small sample sizes. So there's the test statistic for now we'll look at the tests and confidence intervals for the difference in 2 means of normal small sample sizes but unequal variances. There's the test statistic. We don't pool a 2 SX and SY. Now this has been shown mathematically. Have a T distribution. This will be the number of degrees for small sample sizes. So the difficult calculation is actually calculating degrees of freedom. Degrees of freedom are usually integer numbers. This won't be an integer number. What you do is you round to this value. The critical region will be under the t-distribution with this degrees of freedom. There's confidence limits. X bar minus y bar plus or minus t sub alpha equal 2, square root, and this is really an estimate of the standard deviation of x bar minus y. The degrees of freedom is a more difficult calculation. Testing the equality of variances. The test is called the F-test. So you have two populations. We have a sample from one of the populations, that's the X values, a sample from the other population, the Y values. They're differing in both mean and variance. They're possibly equal. We want to test now what the two variances are equal. So there's what we want to test. We want to test whether the two variances are equal against the hypothesis they're not equal, or we might want to prove that one is bigger than the other. The alternative might be a one-sided alternative. The test statistic is not the difference between the two variances, but the ratio of the two variances. Sx squared over sy squared, or the other way around, sy squared over sx squared. Doesn't matter which one you use. The sampling distribution of the test statistic is called the F distribution. It has 2 degrees of freedom, a numerator degrees of freedom, which would be the sample size minus 1 of the numerator, sample size minus 1 of the denominator. So when I switch which is in the top and which is in the bottom, this still has an F distribution, but it has the degrees of freedom switched around. There's a graph of the F distribution. It is on the positive axis because Sx squared and Sy squared are always going to be positive. The numerator degrees of freedom is the sample size minus 1 at the upper, the sample variance on top. The denominator degrees of freedom is the sample size minus 1 of the data that's on the part. The F distribution is a positively skewed distribution, but it's centered over the value. It changes if you change the degrees of freedom. As the degrees of freedom become larger, it becomes more concentrated over the value. If Sx squared over Sy squared has a F distribution, degrees of freedom n minus 1 in the top, n minus 1 in the bottom. If I invert it, it still has an F distribution, but the degrees of freedom are changed around. The critical region for the test, testing whether the variances are equal. If the variances are equal, Sx squared over Sy squared should be close to 1. In fact, it has an F distribution. The alternative statistic is the other way around, Sy squared over Sx. So we're gonna, a two-tailed test would reject if F is greater than its critical value, or the other way around, 1 over F is greater than its critical. critical region in a one-tail test, you use the one that's on top. It's going to indicate the alternative is true. So that's, there you wouldn't divide alpha by 2. Example. In that example where we had 2 groups, where ones that were treated with the drug and the other one that were not treated. Now, in the test that was used, t-test used, it was assumed that the 2 variances were the same. You can test that using the f-test. There's the tests, the estimates of mu1 and mu2, sigma 1 and sigma 2. If I want to test if sigma x squared equals sigma y squared against sigma y x squared not being equal to sigma y squared, this is assumed with the t-test. So this possibly should be done before performing the t-test. We would reject if sx squared over sy squared was large, or the other way around, sy squared over sx squared was large. This is the critical values. Alpha divided by 2, that should be 0.0, not 0.25, 0.025. If it's sx squared over sy squared, the numerator degrees of freedom is 2, the denominator degrees of freedom is 5. 1 minus less than the sample size. If it's the other way around, the degrees of freedom should be switched around. The F statistic is 0.76. 1 over F is 1.32. So both of those are less than their critical values. So we would accept the hypothesis that sigma x squared is equal to sigma y squared. Maybe at this point we will, this is a quick review. There's the 2-sample t-test for testing the equality of 2 means. There's confidence limits for the 2-sample t-test. There's the same thing, but where we don't assume that the variances are equal. Look, the difficult computation here is the computation of degrees of freedom. There's the confidence intervals for the difference in 2 means. Variance is not assumed. We'll go on to some other tests next day. I think I'll stop at this point. And I'll ask if anybody has any questions. So if not, we'll just end the lecture at this point. Yes.
Yeah, so I was just wondering, when will the grades for the second assignment be ready?
Well, actually, it'll probably be a week or so, okay? Because the markers have just gotten them, okay?
Okay.
So it'll probably be about a week or so.
Right, thanks.
Okay. So at this point, I'll just end the meeting.